of the FGI podcast series. My name is Tim Stark, and I'm a professor of civil engineering at the University of Illinois at Urbana-Champaign. On today's episode, we are going to focus on our October 21st, 2021 webinar titled An Introduction to Mechanically Stabilized Stabilized Earth MSE Walls, with the second portion of the webinar covering detailed design calculations in early 2022. I'd like to quickly reintroduce our distinguished webinar speaker, Professor Richard Bathurst, who is a Professor Emeritus of Civil Engineering at the Royal Military College in Kingston, Canada, where he has taught since 1980. Richard has authored or co-authored over 400 papers in refereed journals, conference proceedings, and research monographs. Dr. Bathurst's primary research activities are focused on the use of geosynthetic and metallic reinforcement in earth retaining wall systems, numerical modeling, seismic performance, and design of these systems. Dr. Bathurst is editor-in-chief of the peer-reviewed and popular technical journal, Geosynthetics International, and past president of the International Geosynthetic Society. It is a great honor to have Richard join us for the first of two webinars on MSE walls. And this podcast focuses on a number of questions, 17 questions that we were not able to answer during the live webinar presentation, and some follow-up questions that we received after the webinar. So, Richard, thanks so much for joining us again.
Thank you, Tim.
Okay, Richard, I'd like to start with the questions from the live webinar presentation that we were not able to cover in the hour. So here we go. Most examples seem to show the same strap lengths throughout the wall height. Is this most common, or are differing strap lengths more common?
Yes, this question is actually very similar to a more extended question that occurs later. So what I'd like to do is just bat the answer to this question to a response to a similar question a little bit later in this podcast, if I may.
Sure, great. So let me skip to the second live question. What are the pros and cons to using number 10 quarry screenings in the reinforced backfill zone of metal strip MSE walls?
I'd like to refer first to recommended practice for MSE walls in North America, and that is that the gradation for the backfill should conform as much as possible to a well-graded aggregate, well-graded according to the Unified Soil Classification System. There's not a lot of detail in the actual particle size distribution for this number 10 material, but the fines content should not be greater than about 15%. And also we have to remember that there are other criteria, for example, pH and certain electrochemical property limits that should be respected. And these criteria can be found in FHWA and AASHTO documents. One of the things you like to have is a well-graded material, because it can grab these metal strips more efficiently, if you like. So on a project-specific basis, it would be recommended that this number 10 steel strap pullout condition be tested in a pullout box, so that the designer actually has project-specific interaction coefficients for this particular scenario, rather than simply using default values that you can find in the literature.
Right. Okay, Richard, number 3. How do we ensure the shear behavior between the reinforced soil and the retaining soil?
I think the main factor would to ensure good drainage, so that you don't soften up this potential interface. So you want to make sure that any surface water doesn't migrate into that interface over the design life of the structure. And it's worth noting that a strategy to mitigate this is to put a geomembrane at the base of a surface granular drainage layer. And I showed a slide of that in my presentation. And of course, it's important that both the backfill and the reinforced soils are well compacted. And if there are any, if the phreatic surface is passing into the vicinity of this interface, strategy should be undertaken to make sure that that surface is directed away from that interface.
Great. Fourth question, is it possible that we can provide geosynthetic reinforced soil with integrated bridge system, even for railway bridges where more dynamic loads can be expected?
The answer is yes, and it has been done in Japan.
Great. Number 5, isn't a supplementary facing needed to prevent deterioration of the geotextile wraparound face due to prolonged exposure to sunlight/UV?
Yes, if the wrap face is permanent and exposed, then a protective covering is required. Shotcrete and asphaltic sprays have been used for this purpose. The tall, unprotected wrap face wall that I showed in my presentation was a temporary structure that was used to support the sides of a preload embankment that was constructed to pre-consolidate the foundation soils at the project location. So with respect to deterioration and the like, this structure was not critical from that point of view. However, for any wrap face type wall, an exposed face is always a target for vandalism. And so for that reason, some sort of protective covering may be desirable even for temporary wrap face structures.
Right, good point. Number 6, what is your view on MSE technology for tailings dams in mining operations? This in light of the 2 disastrous failures the mining industry is prone to, certainly in Brazil, but of course, as you know, in Canada, there are others.
Yes, that's right. The famous Mount Poly disaster.
Right.
Based on my understanding of the mechanisms that led to these large tailings failures, the presence of an MSE wall would not have influenced the outcome. The properties of tailings fills will vary widely, and if they are used as part of an MSE wall structure, then the properties of these materials can be expected to influence both internal and external stability of these systems. So you have to design with the properties of these materials in mind if they're going to be part of an MSE wall structure. For example, I was once involved in pull-out testing of geogrid reinforcement materials in an oil sand, tailings backfill material. And in this particular case, the bitumen content of the soil led to much lower pull-out resistance than would be expected for the same soil without a bitumen content. So the take-home is make sure you know your materials in the context of the design of these MSE wall structures.
Right, good site-specific example there. That's great. Yeah. Okay, next, number 7. A few months ago, the FGI presented a webinar for the MSE wall that moved at the West Virginia airport. Actually, Richard, as you probably know, it was a reinforced soil slope, not.
That's right.
Yeah, exactly. For the next webinar on MSE berm, would it be possible to cover that one from an MSE wall design perspective? That is, what could be done better? I recall that the remediation did not involve MSE. That's correct. It's a geofoam solution. So may want to add a discussion in the presentation regarding water building up behind the wall, drainage behind the wall, etc. So I'll let you run with that very open question.
Yeah, it is a very open question. And the short answer is that in my next webinar, I'm going to be dealing with issues related to good design and construction practice, and the importance of controlling water, for example, and any other types of external events that a wall has not been designed for. As we know, it's or as common experience now suggests that it's the things you don't know and the things that happen to a wall that were not known at time of design that cause them to misbehave. And most times it has something to do with water. So I will discuss those issues in my next webinar.
Great. Okay. Number 8, is there a rule of thumb of what the deformation of the MSE wall will be, for example, to active earth pressure or some other condition?
Yes, predicting wall deformations is difficult, particularly as deformations are very sensitive to the type of the wall and construction quality and all these and similar things that you just can't put into an equation. There are publications that provide guidance on specified and expected wall deformations for well-designed and constructed walls. So for those conditions, typical wall deformations tend to be in the range of 1 to 2% of the height of the wall. Again, these are for well-designed constructed walls. I do have a paper that I will give you, Tim, that you can post on the webinar site that provides a summary of the typical expectations and specifications for wall deformations that have been published in government guidance documents and in the published literature that people can refer to. With respect to the comment about active earth pressures, it's a common belief that the earth pressures in the soil reinforced soil zone are at an active state everywhere under operational conditions. Okay, the conditions that we're designing for the life of the structure. And I respectfully submit that this is a myth. The reason is, or the justification for that comment is that the calculation of loads in reinforced layers in geosynthetic MSE walls using the latest stiffness method, which is in the AASHTO code, and also the coherent gravity method, which is used for steel MSE walls, the loads are based on backfitting to measured loads rather than the assumption that the reinforcement loads must resist active earth pressures. So this idea of active earth pressures is not valid, and the proof is because we don't use it, because it's been shown not to give accurate results. And in my next webinar, I will talk about this issue and the main features of the current design methods for calculating loads in geosynthetic and steel MSE walls.
Right. So Richard, the measured loads are correlating to something higher than active earth pressure. Is that, I think that's what you're saying?
It depends on whether it's an extensible, that means a geosynthetic wall, or a steel. So what we tend to find is that the loads actually that people have predicted in geosynthetic reinforcement is actually much higher than what people have observed. And in fact, it can be up to even 30% higher. And this means that these designs are somewhat conservative. And also what happens is that you tend to put the reinforcement in places that it may not be needed. For the steel case, the reinforcement loads are definitely higher than what you would expect for a deformable system, because steel is very stiff. And so you can't use active earth pressure at all. And when people were inventing, for example, the coherent gravity method for steel MSE walls, they went straight to their library of measured results and empirically, or came up with an empirical design method so that the loads that have been measured in these structures matched the predicted loads for design.
Excellent discussion. Great. And for the listeners, we will post this paper on deformations that Richard will send with both the podcast and the webinar. Okay, thank you. And now let's go to number 9. As a follow-up, I see designers not doing any real design on leveling pad or base for MSE, but they do design soil layers and geotextiles. Shouldn't be a problem, but we tend to not see the base material being evaluated like a normal concrete wall would. Focus on backfill material versus lower is the overall question. So maybe just a bad design use versus method being good. I'm not sure about the last part, but if you could talk about the leveling pad.
Right. I think, for flexible modular block walls, it's common to use a simple leveling pad, or maybe a sort of a concrete mud pad. And part of that is because these modular block walls can tolerate differential settlements more than walls with concrete panels. But for walls with concrete panels, you have to have some sort of concrete footing, because it's really important that those panels are well supported and seated, or else you can end up, in some worst cases, you can get a situation in which the panels will impinge on each other and you can get cracking and spalding. In either case, the calculations to ensure that whatever type of leveling pad or footing you have, those calculations are quite simple, and you can design them based on conventional, bearing capacity theory, for example.
Right. Okay, great. Last question from the live webinar. Is a geofoam cushion placed against a wall good for multiple earthquakes, or does it just have a one-time use? Does all the compression get used up on the first earthquake?
That's a very interesting and good question. The seismic buffer must be designed to stay within the elastic range of the material for the design earthquake. And the way that you do that is you choose a suitable thickness for the layer. So that geofoam layer, inclusion behind a rigid structure, it can be, a third of a meter up to a meter, depending on the height of the wall and the intensity of your design earthquake. There are specially manufactured geofoam materials that are elasticized during their manufacturing, and these increase that initial elastic strain range that you need to stay within. So there are design charts available. In fact, I published a paper, which I'm going to include in my package to you, Tim, that shows how you can select an appropriate geofoam material based on the height of the wall and the intensity of your design earthquake.
Great, fantastic. Okay, Richard, now I'd like to shift to the questions submitted after your live presentation, and we have 7 of those questions. So, number 1, are the strap lengths typically variable with wall height or of a consistent length? Similarly, does density of straps change with height? And this is where I think you'll answer both of these questions.
That's right. So the minimum strap lengths in design guidance documents and codes are prescriptive. In other words, regardless of external stability calculation outcomes, they're typically not less than 60 or 70% of the wall height. And this prescriptive rule often governs the internal arrangement of the straps, and it's the reason why you see many walls with uniform reinforcement lengths. However, for straps, be they steel or polymeric, these materials are placed with a low coverage ratio. Okay, so when you have a geosynthetic, it's a continuous sheet reinforcement. But when you have a strip or a strap, it's just a thin slice. And because of that low coverage ratio, it's not unusual to have to increase the length of the straps at the top of the wall in order to have sufficient pull-out capacity. Now, with respect to the density of the straps, and here we're talking about the spacing, it's not unusual to have a smaller spacing of reinforcement layers if you're using the same reinforcement type up the height of the wall, to have a smaller spacing with depth, because the loads in the reinforcement tend to increase with depth. So one way to mitigate that is to decrease the spacing of the reinforcement, so the share of these lateral forces to be carried by the reinforcement layers are appropriate. The other strategy is to keep the spacing the same, but as you get deeper into the wall, greater distance from the crest of the wall, is to use a stronger material. And in that wrap face wall that I showed that was very high with the exposed facing, there they had different reinforcement types as to get deeper into the wall, and those reinforcement types had progressively larger strength and stiffness.
Great, excellent. Okay, number 2, from a failure standpoint, and our geotechnical consulting firm has been involved in evaluating 14 MSE wall failures. Would you agree with the following factors contributing to failures? Number 1, poor construction. Number 2, poor design. Number 3, material defects.
Right. Yeah, these sort of an overall yes, I agree, but I'd like to clarify that. Poor construction is an easy one. Poor design, I'd like to just say that the basic design principles that are used for external and internal stability of these systems are sound, but you have to make sure that the conditions that you're using for design and appropriate assumptions apply to those design methods over the life of the structure. It's, as I mentioned before, you can have failures because the structure is subjected to conditions that weren't considered. Water is frequently the cause, or it could be something as simple as a large ground shaking due to earthquake. So you have to qualify what you mean by poor design.
Yeah.
With respect to material defects, I should point out that geosynthetic and steel reinforcement materials are highly engineered materials and very unlikely to have material defects when they leave the plant. But of course, these materials must be handled and installed correctly on site to prevent damage, so that the properties of these materials that you paid for arrive on site when the structure is built.
Right. Richard, maybe just a follow-up for this one. What about a live load on the top of the wall not being considered in the design process? Is that ever an issue, or is that taken care of with reinforcement?
Well, yeah, it should be considered, and if you look at design guidance documents, there are recommendations on how to handle those live loads. What they tend to do is use the live loads on the destabilizing side of your calculations, but don't use them on the resisting side. And this tends to give a safe outcome in your calculations. Often with live loads, for example, if you're considering a pavement or road pavement or the like, there are some rules of thumb how to convert those live loads to an equivalent uniform surcharge pressure, 12 kPa or 14 kPa or something like that. So there are rules of thumb to handle live loads.
Great. Okay, number 3, is there a study on the use of backfillers with friction angle less than 35 degrees, or what can we do when it is not possible to find backfill with the desired gradation and, I guess, shear strength or friction angle?
Right. Designing and constructing MSE walls with lower friction angle soils is possible. And indeed, it's done routinely in countries where only so-called marginal cohesive frictional soils are available. Much of North America, we are blessed with high quality aggregate sources, but in many other countries, this is not the case. But if you do use these so-called marginal soils, you need a knowledgeable designer and a competent and experienced contractor. But when you, for example, in Japan, they use soils that they use cohesive frictional soils that fall outside of the recommendations that you find in current North American codes, but they design them carefully and they construct them carefully, and they have behaved very well.
Great. Okay, next, number 4, what can be done to maintain MSE wall stability if an excavation is required near the wall base, for example, urban environment utility work?
Any strategy to support the base of a conventional retaining wall would also apply to MSE walls. I mean, from that point of view, there's nothing different. The MSE walls are not magic carpets. Okay, they need the same sort of support for the life of the wall as any other type of retaining wall would require.
Okay. Number 5, what is the fines content limit for the reinforced backfill, for example, the fill over geogrid, where an additional aggregate drainage layer would be recommended?
Yeah, I wasn't quite sure about this question, but let me just start by saying that typical recommendations, such as the ones we find in AASHTO and FHWA, have restrictions on the maximum fines content, and that's about 15% fines, and a lot of that has to do with ensuring that the fill is drainable, if you like, and also constructible and the like. Now, in some cases, fines contents up to 35% have been used in the design of these systems. And also you find, again, in some countries where they don't have the high quality fills that are more available in North America, they have also used high fine contents. But again, this requires careful design, and it certainly requires careful construction.
Right. Okay, number 6, is it possible to add secondary layers of geogrids, or maybe just reinforcement, between primary layers to help the connection performance by decreasing the concentrated loads or pressures at that zone, or I guess the face?
The answer is yes, and there has been some work done on this issue. However, it's difficult to know or compute the reduction in reinforcement loads in the primary layers that are transmitted to the connections using this method. One strategy from the design point of view is to, if the reinforcement spacing is low enough, is to treat the facing plus these short secondary reinforcement lengths as an equivalent wider composite facing column. Because as the facing column becomes wider, this will reduce the load demand on the primary layers. So that's one strategy to calculate the benefit that may be possible on connection loads using these intermediate secondary layers.
Right. Okay, Richard, last question. Thanks for hanging in so long. This is a good one. What is your take regarding the use of high modulus geotextiles as reinforcement?
There's no practical reason why high modulus geotextiles can't be used to perform the soil reinforcement function. They may have some advantages because they're stiffer and stronger. So if you want something that's stiffer and stronger, then these could be available to you. So no practical reason why you can't use them.
Great. Well, thanks so much to Richard Bathurst for joining us again, and we look forward to your second webinar on design of MSE walls, hopefully in early 2022. If you have any additional questions or would like additional information, please send your questions in or email to Professor Bathurst at bathurst-r@rmc.ca, or you can download his webinar slides from the fabricatedgeomembrane.com website, and his email address is on the title and the last slides. So, Richard, thanks so much again, and we look forward to your second webinar.
Thank you, Tim, for giving me this opportunity, and I look forward to giving this webinar, like you said, early next year.
Great, Richard. Thanks so much, and best wishes for the end of the year, and hopefully we'll see you in early 2022. Thank you.